Hello guys. Going back to what we were discussing yesterday as the last topic, I just moved the last part of the definition to this new file, so to have grouped all the topics that we are going to discuss today, which will deal mostly with a particular behavior which is called differential growth. What we are going to do now is basically go back to our rectangular plane and let's say random organic shape. Remember that the only thing that we were discussing yesterday was that this curve must not self-intersect initially, so you just have to tweak the seed if you want to use this kind of random generation here in order to don't have a self-intersecting curve. We saw yesterday how this curve can expand inside this area by converting its segments. Remember that we rebuilt this curve and converted these segments into springs, and also creating some collision between its vertices. Now you see that here I added this curve index. The reason why I added this curve index with respect to yesterday's definition is that what I want to do actually is work with a closed shape in order to have this closed shape expand inside this region, so we don't have loose ends like in our design. So the only thing that we must do here is convert this NURBS curve into a periodic NURBS curve, like this one. And of course, we could also work with a standard circle. The problem with the circle is that if the circle starts to expand due to collisions or to spring behavior, initially the circle will expand uniformly because it is a totally symmetric curve. While it's better for creating this kind of of design to work with organic shapes, because eventually you will have an irregular expansion of this curve. Probably it will be more important in these areas where curvature is higher, and it will be smoother as behavior in this area where the curvature is lower. Okay. This curve index here is necessary because of one particular thing. Let me show you this. So I'm going to switch this back to the default vertices, and when I run this simulation, Kangaroo just detects an error. Okay, and the error, in order to let's say debug this script, we must think about what can happen inside these goals, because Kangaroo can only receive errors via these goals, right? So show is just showing the original segments, so it cannot produce any error. Okay. The springs are actually extending and expanding or contracting. So, actually, also in this case, errors are very unlikely to happen. Also, collision are not happening at this moment. So, at the beginning of the definition, there would be no reason for collision to produce this kind of error. So, the error must lie inside the collider, and we are providing vertices to this collider as objects. Okay, and if you take a look at the list of vertices that comes out from this explode, you might notice that the first value is exactly identical to the last value. And this is because we just converted our NURBS curve into a periodic NURBS curve. So the start point and end point are coincident. And once you explode that line, then you will have two coincident vertices. So the collider is trying to create a collision between two coincident points. And so this is generating the problem for Kangaroo. Kangaroo cannot solve that collision. And so here I just created this call index. As the two values that are repeating are the first and last, it's easier to remove the first value by calling index 0. So actually in this list, the first point, which is 422,669, which is coincident with the last one, is just gone. Okay, and so you have a periodic curve, but the start point end point is just being considered once in this list. And you will see that in this case, things are working properly. So Kangaroo can calculate this simulation. Now, you saw that the expansion in this case was quite, let's say, fast. I don't recommend that you do this. This is because I left the multiplication factor to 4, and the radius for the collider is already receiving a high value for collision. Just so that you remember, we are using a closed curve with 600 segments. Okay, and so if you take a look, for example, at the length of these segments, if we analyze, well, let me get rid of this group. So if we stop the simulation for now and then go and analyze the length of these segments, you will see that the length is very, very small. So it's 0.07. Okay, and even if we multiply this during the simulation by 4, you will have basically 0.28. So it's very small. And we are saying that the collision radius is more or less 3 times the size of the segment. So we are pushing each vertex 3 times farther than the original position with respect to the closest vertices. So this curve is expanding quite fast. I don't recommend you do this. Now that we know that the length of this original segment is 0.07, we can also get rid of this multiplication, because what happens is that if you work with this length factor here, even if you work with a high value like 4, you are multiplying the original length by 4. Normally this design is made for occupying a specific surface or a specific area with specific dimensions. So the resulting rest length in this moment depends not only from the length factor, but also from the amount of segments that we want for our polyline. Because if I increase the amount of segments, I will decrease the length of each segment. So even multiplying that length by 4 will always give us a smaller rest length. So instead of working with this multiplication factor here, we could also work with a standard slider, where we can easily determine what's the smallest possible length for our segments. Could be, considering that actually it is 0.07, let's say that if we also increase the amount of segments, this could also reach something like 0.01. And we can also state that the highest value for this length, considering the size of our geometry, and consider that we have already 600 segments, if we give this value a upper limit of 1, we are already considering quite a important rest length. So let's say we give this 0.01 to 1. And now saying 1 is actually 4 times stronger than saying 4 times the actual length, because 4 times the actual length is more or less 0.25. So 1 is already 4 times bigger than this actual length multiplied by 4. So this value is already a big value for our simulation. Okay, so I will reduce this, for example, to more or less 0.2. Let's say that in this case we are more or less in this range, and I will substitute this slider in the rest length. Okay, so if I do this, I simplify this part of the simulation, and you see that I am shrinking a little this elastic body here. So I have a more direct control, because if I now move this, you see that the curve reacts immediately, okay, to these small changes, because this is determining exactly the physical length of each segment of my line. Okay, so you see that everything now reacts so fast. And the other problem was that even if I go back here to 0.25, let's say so, if I reset this, you see that this curve is exploding actually. Now, I do not recommend this also for another reason, because the collider, well, actually, yes, it keeps each part of the curve away from another part, be 2 consecutive vertices, also 2 vertices getting too close together. But also it produces a very fast expansion, and these could eventually make the curve self-intersect during the expansion phase. So you see that during the expansion phase, there is a lot of chaos going on. And sometimes you might detect that in some areas, for example, here at the bottom, the curve self-intersects for a while and then just, and also here in the top left corner, there is a small self-intersection, but then the curve manages to smoothen its path. Now, this is totally random, so I wouldn't rely on the fact that the curve will take a proper configuration towards the end of the simulation. So I do prefer to control the initial part in order to avoid self-intersection. So in this case, for example, I would reduce the expansion speed by reducing the radius, the collision radius. You see that we still have some self-intersection going on here. That's because in the initial instance, the expansion determines this self-intersection, and once you get this phenomenon here, it's very difficult to get rid of them, even tweaking the values of your goals. So eventually here we can start with smaller values and reduce the speed of this growth. But you see that in this case, for example, even if the rope or this body is expanding slowly, also we could decrease this, because remember that we are instantly switching between 0.07 to 0.2. So it's more or less 3 times bigger the actual rest length than the original length. So this body is expanding quite fast also because of the length line. So let's use some, okay, so we know that our segments are more or less like this, okay, so 0.07. I'm just introducing a small value for the collider. So remember that initially we have one vertex here, another vertex here. The distance is 0.07, and I'm saying that I want a collision radius of 0.11. So this is taking basically this point away by 0.04 units. Okay, so it's a very small expansion factor. So if I reset this, I start to have this kind of behavior. The curve starts to grow very, very slowly, but I am sure that in this case I am not getting self-intersection during the expansion phase. Once I see that the curve tends to reach an equilibrium phase, then I can start working with this parameter in a more, let's say, effective way. Okay? Because now the goals are already in control, let's say so. Okay, so you see that now we are starting to get some nice distortion, and this thing is starting to grow, but we are already working with some controlled collisions and controlled length, and so we can expand this organic shape inside our area. Now you see that as we are expanding and adjusting the a polyline, the amount of segments, well, actually we already have quite a huge amount of segments. There are 600, but you also see that they tend to, well, behave like polylines. So you always see these vertices and these segments, which are basically assuming a random mutual inclination or angle. So what we can do here is eventually try to smoothen this curve. Now, there is one aesthetical smoothing that you can do after the simulation has determined the final result. So you can take this, well, remember that we send to the show component each single segment. So you have individual lines coming out from this exploded tree. So we must join them together in order to obtain one single polycurve, and then we can rebuild this curve back, but this time we will use a degree of 3 in order to produce an organic shape. And what I'm going to do, I'm going to use as a count, number of control points. Well, we can also use the amount of vertices of the original polyline. This will necessarily give us quite a good representation for our NURBS curve. Now you see that this is starting to give us a smooth curve, but you also see that the smoothness of this curve depends basically on the inclination between two adjacent segments in the polyline. Okay, this is not a real smooth curve because you always have this kind of variation, curvature variation, constant curvature variation along the path. This is due to the fact that we are basically placing or tracing this NURBS curve based on a polyline. Now, what we want to do instead of doing this, I'm going to get to go back to the original preview. Instead of doing this, and we still have the simulation running, so I'm going to stop it right now and reset it, and go back to our initial values, which were more or less 0.08 and 0.11 something, or yeah, it shouldn't affect the simulation too much. So let's double check that everything works fine. Yeah, no self-intersection. So what we can do in this case is basically smoothen this line. Now, how can we do this? In this case, in Kangaroo 2, we have this Gold's angle group. And Gold's angle group allows to define or to smoothen a line by several different ways. So what we're going to do right now is use the simplest one, which is angle. But you can also, for example, double check and investigate like something like clamp angle, or no, sorry, or angle snap and so on. Okay, but angle, it's the simplest way to achieve this goal. I'm going to use this goal here. This is a non-geometrical goal, so it will be connected to the same input as the collider and the curve point collider. So they are all constraints basically, and I will move this here eventually, so collisions are going to stay together here, and I'm going to tweak now the angle condition. So angle must be set between two segments, and all of our segments are here. So what I need to do is adjust the angle between segment 1 and segment 2. Now, how can I do this when I have both line A and line B inside the same segment list? What I can do is use a shift list component in order to shift the segment position inside this list into another list where the segments are shifted by one position. Okay, so what I'm going to do, I'm going to use a shift list component and shift list the list of segments. The shift is automatically set to 1. So it means that the first segment of this, the first segment of this new list is actually the second segment of this first list. Okay, and so I can easily set the angle between one segment and the following segment. Okay, and also the shift list has this wrap input which is set to true. As we are working with a closed curve, it says that of course if you shift the elements of one list by one position, what happens at the end of the list? So in this case, the end of the list will receive the first value of the original list. So this guarantees that we will also be adjusting the angle between the last segment of this list here and the first segment of this list here. Okay, so this is, if you don't set this wrap to true, you will miss one angle at the beginning or end of this closed loop. Okay, and so rest angle is as most of all the angles in Grasshopper is measured in radians. The problem is that in this case, this component doesn't allow automatic conversion to radians or to degrees, so you must use a radians component. And now we can specify the angle, we can set the angle in degrees. I will use an angle between 0 and 90, 90 being already quite a huge value for the angle. So remember that we are trying to smoothen this curve, but it will also be interesting to consider and to watch what happens when we force the angle between two lines to be a specific value. Okay. Remember that this is not setting a limit. This is actually forcing two segments to form an angle with exactly piece value. Well, of course, according to the strength that we give to this component here. Now, soon after implementing this behavior, we are going to talk about the strength of these things here. So if I now run this, the curve starts to expand a little. You see that it's adjusting its shape, but now there is also a limit for the inclination between the angle between two segments. So you see that this, for example, this part that was expanding downward is no longer expanding because the expansion will alter the angle between two segments. Okay, so in order for this to become, let's say, visible again, I must increase these values here and make their action stronger than the resistance of the smoothing that we are creating right now. Okay, so increasing these two values will tend to expand the curve, as we know, but you see that this acts like some resistance to the deformation. You see that this curve is already expanding, but you no longer see that kind of vibration during the expansion. You mostly see this kind of blobby figure coming out of this simulation. And you see that the simulation always starts slow, and then when it becomes fast, it tends to accelerate a little. That's why I suggest you keep these values as low as possible in order to start seeing some deformation. When you start seeing deformation, even if it's very small at the beginning, don't increase these values too much, because else the acceleration will be too fast and you might get some self-intersections. So you see that these things start to adjust smoothly. Eventually it goes over the boundary because of the strength of this gold. We are going to adjust strengths in a while. Oh, actually, we can also start doing this in order for this curve to remain on the inside. So I will take a 101 slider and set it as strength for our boundary. You see that it instantaneously pushed the curve away, and this became unstable. Okay, so you see this is also something that you might want to do at the beginning. Okay, so to avoid instant deformation. Instantaneous deformation are those phenomenon that bring instability inside the system and might cause some self-intersection or some, let's say, resonance in the oscillation on the vibration of this system. And so basically it becomes unstable, and Kangaroo is no longer capable of going back to a controlled situation. But you see that now this thing is behaving properly. It doesn't go out from the boundary. You can double check also in this point here where it's getting quite close. Here it is. You see there is some, let's say, the curve is adapting, but it's no longer bouncing like in a violent way. Also here you will see it will be more gentle, and therefore the system is evolving, right? Now, when we introduce the angle, we must also understand that the system is it's very difficult for this system to reach an equilibrium, because you will notice that Kangaroo will keep on running and running and running without getting to a converged scenario. Because what happens with the angle is that the angle tries to force two segments to have a mutual zero angle. Okay, so it tends to straighten up this line. So if you consider the zero angle means that two segments are perfectly aligned, right? And if two segments are perfectly aligned, you couldn't get this kind of curvature, right? So this actually, this force, this goal, is actually working against the elastic force and also the collider. So these three things here are working in the opposite way. So there is always a struggle between these components here, these goals. And so you would see that the curve tends to, let's say, deform, and this deformation will affect at the same time all of these three guys here. It's like, for example, having quite a rigid body, a rigid, I don't know, something like well, not an elastic rope, but I don't know, something like, yeah, I am watching right now the cord of my mouse. So it's like trying to compress an object that cannot be compressed, so it tends to suddenly bend in one direction. Okay, so this is what happens here. But this bending is constantly evolving, right? So this simulation is very difficult for this simulation to reach a final configuration. Okay, and the speed of this depends on how strong these components are. So you saw that in the as for the curve point collider, I placed a slider with 101 and able to reach up to 1000. And now 1000 is might be too high. It might produce some instability. Um, but eventually, you see that I use this for the curve point collide because I want this curve to be, let's say, quite a strong limit for my design. Okay, I don't want the curve to go out from the square. You see how it is constantly evolving, especially in this area. But anyway, so 101 for now is good enough. I only see that here something is not perfectly right. Okay, but it's basically nothing. What about the other goals? So you see that, for example, the fact that we set a zero angle and we get this kind of curvature here is because this angle here is not strong enough. Also, we are saying that these springs must reach a length of 0.23. This is something that actually can happen because we have no other boundary than the outer border of our surface. So inside the surface, this line can deform as it wants. So these lines, these springs can actually reach this kind of length. And if we take a look at the result here, these are the lines. We can easily calculate the length and take a look at these values here. And you will see that they are more or less around that value. The fact is that we have the springs that want to reach to this rest length, and then we have the collision radius, which is 0.37. So we might have some springs that have more or less 0.23, but also some springs tends to have something like 0.30 something. It depends on also on the angle that they are forming. Okay, between the angle and the collision radius, then you will have the actual length for our spring. But if we want the springs to have exactly this length, then we can increase the strength of the springs. So even if we have a radius, a collision radius of 0.37, if we place a 101 slider to these springs, you will see that this curve tends to shrink. And now if we go here, you see that these lengths are getting closer to the 0.23 value. Okay. The same thing with the other parameter. So of course, these two parameters here, these two forces here, if you want the length of the springs to be exactly this one, also the collision radius must be that exact value. Okay. Else you are going to have two opposite actions for this object. So let's also increase the strength, for example, of our collision radius. This tends to expand the curve again. And also the angle. Now, the angle, in this moment, you see that the angle is absolutely not capable of straightening up the whole portion of this curve. But this is not the point. The angle is not needed to align two segments. The angle is needed to smoothen the curve. And you see that we are already getting a smooth curve. So in this moment, I wouldn't work with the strength of the angle, okay, because this result is already smooth enough. And we get this nice pattern that are evolving inside our shape. Of course, if I set the collision radius to 0.37, I cannot have 0.23 like the rest length. Eventually, this curve will stretch a little more as regards the collision between one vertex and the next one and the previous one. But this collider is also affecting the collision between different portions of the same curve. So you see that this is kept at this distance more or less from the other portion, which is this one and this one, okay? But if I increase the rest length, I can extend this curve much more than now. And this will not be in contrast with the collider. So if I increase this value, this curve can still extend and fill this area more and more and more. The only thing I do recommend is that when you increase these values, whatever value you touch inside this simulation, just change these values very gently, because you want to avoid instability. Okay, so you see that we start to get this kind of nice behavior. Let me also point out one thing, which is this. We also have our high resolution or smooth curve. We can also use the two concepts together in order to have the smoother possible curve. Okay, and once you have this, if you want, you can also easily connect this to a boundary surface and create this object here. I don't recommend that you do it in real time, like while the simulation is running, because you might notice that this component starts to have a profiler. Okay, it means that it's taking some time, even if the huge amount of calculation is done by Kangaroo. But this is something already. Okay, so I wouldn't do this in real time. Also because when the simulation becomes unstable and when you have some self-intersection, this component would fail. So at the beginning, you might want to keep this off by default. Okay, and just take a look at the smooth curve and also degree 3 curve. Okay, which we get from the revealed curve. So this can be just one nice result already. Now, one other thing that we can do with this is the following. If we, of course, if we decrease the collision radius, this curve tends to let's say, different portions of the curve tend to get closer together. So as you can see here, but this is also a problem, because if the separation between points is high, you see like this, and you are considering a collision radius of 0.14, what is happening right now, and I'm going to stop the simulation, is this. I have a vertex here, vertex here, vertex here. They are being smoothened by the angle condition, and then another part of the curve comes here and eventually has these vertices. Okay, now the collision radius could be something like this, because it's actually very low, sorry. And so basically this point can pass between these two, and this point can pass between these two, and so you have intersecting portions. Okay, so this is something that you eventually would want to avoid. Okay, and once you have self-intersection, I repeat, it's very difficult that you can get rid of them, as you can see. Okay, now this pattern here is no longer, let's say, regular, of course, but this is still a graphic design which has some nice aspect. Okay, just in terms of design. So for graphic design, not necessarily you might want to avoid any type of self-intersection. So let me go back to our initial values, like this. Let me reset this. Let me run it again. Let's create some initial deformation. You see that now it's easier to keep things under control. The presence of the angle go actually tends to accelerate a little, in this case the deformation, because it's like, I repeat, trying to deform a rigid or a stiffer body. Okay, so once it starts to deform, the elastic behavior propagates along the shape of the line. So it depends mostly on the strength now in this moment. Okay, so having introduced the strength is actually increasing the speed of the deformation. So once we have this line, I want to have a, let's say, more let's say, interesting behavior, like, yeah, for example, something like this. So let's start to expand this curve a little more, and also increase the collision radius, because remember that if you don't do this, the curve might self-intersect at some point. Another thing that we can do is, okay, now we have this angle control. What happens if we increase this value? Remember that this angle here is tends to be a fixed angle between all couples of segments that you have along your polyline. So if I start to increase this, what I'm saying is that I want two segments of each pair of segments of this polyline to form this angle. And you see that this is changing the shape of the curve. So you no longer have that smooth aspect that you had a few moments ago. You start to have this curvature here. Now, why don't you have pure angles? Because the strength of this angle is set to 1. So it's nothing if compared to the other goals. Okay? And yet you see that there is this kind of deformation. Now, if I increase this value, you will see that this curve tends to become curly. You see something like this, like mushroom coming out from along this path. And suddenly, when you reach some high values, you start to form this kind of curves along the path, like here, here, here. You see, and the higher the value, the more these twirls will start to, let's say, twist and twist. And so we are getting this kind of behavior. Now, why we still have this smoothness? It is because of the strength. Okay, so if you want this behavior to become relevant inside your simulation, then you might want to use a strength, let's say between 1, which is the actual value, to 100. I'm going to increase this gradually, so we will observe the difference. So when I start to increase this, I make the angle stronger and stronger and stronger. Okay. So you see that the main effect is actually that the twisting is going on and on because it is becoming stronger. Okay. And also we have lots of segments right now. Eventually, later on, we can decrease the amount of segments and have a look at what happens in that case. But you see that now the angle is playing an important role because the twisting has become quite relevant. In these areas here, the tension of the curve might be stronger than the the collider. So you might want to give the collider, well, too much. You see that instability happened in that position and everything is just gone. So when this happens, you have to reset the simulation and also go back to your previous values. Okay, so I'm going to do this like this and let this curve start doing its job. Also, don't give too much strength to this value, else it will avoid or contrast the expansion of the curve initially. So once you start having something like this, well, you can start increasing also the angle, but I do recommend that the collision in this case should be higher. The collision radius should be higher in order to avoid self-intersection in the curly areas, because the curly areas are stretching the segments, and so the separation between the vertices is becoming bigger, and therefore you might want to increase the collision radius. And so we start to obtain this kind of graphics here. Okay, so it's very nice to play with this kind of algorithm. You can create some very complex behaviors. There are also famous designs based on this reaction diffusion. Also, a very famous one is called the Thales chair. It's basically you want to extend the lines and you want to decrease the angle back to 0 in order to smoothen this curve. You see that I'm always very gentle when I change these values because I want to avoid sudden self-intersection. Then I'm going to increase the length of this line in order for this pattern to occupy all of the surface available, like this. We start to have a reaction diffusion behavior, very visible, like this. And then I start reducing the collision radius. So if you start reducing the collision radius, you make this curve capable of being very close to its different portions, right? So you start to have this kind of behavior here. where smooth parts of the curve tends to be almost tangent to other parts. And this thing is going to keep on evolving and evolving. And if you increase this, for example, you force this curve to smoothen up. Oh, sorry, you saw that here I also generated a self-intersection. So that's because I reduced this value too much initially. And yeah, I'm not going to get rid of this self-intersection. But anyway, I think you get the point. You can play around with these values and get several different types of reaction diffusion behaviors. Okay. Now we are working inside a planar region, a square basically, but we can work on whatever type of shape we want. So, for example, next step. Let's work with these, and in the end it's going to be almost the same. So what I'm going to do, I'm going to add another branch to my entwine data tree, and actually what makes our design happen inside the square is this curve point collide. Okay. Also the only thing that's relevant in our design is that the only thing that's affected by this square is the collision here and also the creation of our NURBS curve. But what I'm going to do right now, I'm going to take this curve, send it to this container, internalize the value here, and use this as our curve. Okay, so the NURBS curve is no longer dependent from this square here. And so I can get rid of the populated 3D and the NURBS curve itself, and eventually, if I want to work with this collision, I will have it available here. Okay, so this is going to be one option for us for our reaction diffusion behavior. Okay, the other option is going to be a random surface. Okay, so what I'm going to do right now, I'm going to create a deformable surface like this one, and I'm going, as always, to activate the control point and select all of them and soft move them in order to create some organic deformation like this one. Okay, and I'm going to import this surface here, set one surface, and here it is. And also I'm going to internalize this value, so I no longer need the surface in Brine. Now what I want to do, I want this curve to basically deform on the surface. So in this case, for example, what I would do would be to project. Now there is two project in Grasshopper. One is project an object onto a plane, which is not what we need, and the other one is project a curve onto a VREP. And we want to project our curve onto our new surface. Okay, and so I want to work with this curve actually. And so I take this curve. This curve, I don't know if you're let's say aware of this. Eventually, those who have studied some NURBS topology might know this. But when you project a curve, even if it's a very simple curve with a small amount of control point, remember that we created this by a small amount of control points, random control points inside the square. So they are just 8. But if you analyze the projection has a whole set of control points, 100 and 0.5, and they are extremely irregularly, unevenly distributed along the path. So this is a very irregular curve. Okay. So once you do this, we also have to rebuild this, and rebuilding it's not a let's say something that it's unwanted to us. Actually, not only we need to rebuild the curve in order to create this behavior, but we can rebuild it in order to regularize its topology. So if I take a look now at the control point of my rebuilt curve, they are evenly distributed along the path. Even if they are hundreds, okay, it doesn't matter. We have a more regular topology. Okay. So this is actually the curve that we are going to use. It is already projected on this curve. And what I want to do, I want during the simulation, I want the vertices of this curve to lie on the surface. So I go here, for example, if you go on these goals here, there is a goal that is called on mesh. Okay? So what I can do, of course, now I have a surface, so I can mesh surface this one, give this mesh a higher resolution via 211 slider, so I can increase the amount of polygons. Okay, there is no particular need to keep this polygon extremely low, because this mesh is not going to change. It's going only to be used for projection, basically. So I would prefer to create a quite a high resolution mesh in order to have a better representation of my original organic surface. Okay, and therefore I'm going to use this mesh as the on mesh target. And in the end, what I want to keep on this mesh are the vertices of the organic shape that we have here. And so I would take these, that would be the alternative goal. And eventually, what I can do, I can create a switch here. So this is a kangaroo goal. It's called curve to the point. And the other one is called on mesh. What type of data are these? Well, actually, they are simply there. So I can basically create a switch by selecting what collision object do I want to use, and I send it to a separate branch. Okay, so I avoid connecting this to this, and I have a separate branch for these two options. So if I want to work with the square, I use this. If I want to work with the on mesh, I use this one. Okay, and then I created this. I call it the switch. Normally, I give also a yellow color to this one, so I can recognize where I can, when I have different options for my simulation or my script in general. Okay, and so we have our surface, our mesh. Finally, on mesh, also on mesh needs some strength, because if it has not enough strength, if compared to the other goals, the curve might simply take off and leave the surface. So I'm going to visualize the original surface because it has no polygons inside, and let's see what happens. Okay, so let's see what happens if let me double check that the values are quite low. Well, this is already too high, and the radius is quite good, and the angle is 0. Okay, so let's see what happens here. See that this curve is expanding like before, but it now sticks to the surface. Okay, so we can cover any shape with this kind of script, or with this kind of shape. Okay, so and for example, now that I have this curve quite smooth and open, I can also work with this angle directly, and you see how this is becoming crispy and like a polygonal curve. Okay. We can also increase the size of the edges in order for these polygons or these sides to become wider and wider. So this is a totally different aesthetics with respect to the first one. So we have this kind of puzzle happening onto surface. When you increase the length too much, then the angles start to take action and tends to smoothen the small segments and smoothen the aspect of this curve. Okay, and this is happening in 3D on our surface. So you can apply this technique for designing on every surface that you might want to use. The only thing is that as this on mesh works exactly with a mesh, then actually the easiest way to create a controlled mesh in Grasshopper is to use the mesh surface. There is also a mesh brep, but the mesh brep generates an irregular topology normally, while in this case you have this perfectly controlled topology made up of just quads. So you see a totally different aesthetics for the same script. Let me turn off this, reset it, and go back to smaller values, and also to smaller values for the collision radius. Okay. just to double check that everything is, oh yeah, and by the way, the angle. You see that also the angle must be set to 0 initially. And so yes, we are getting this nice behavior. So normally this configuration here makes it easier for this curve to initially be formed, because not only it has some variable curvature along the path, but there is also a three-dimensional curvature for this curve. So the angle actually is working in 3 dimensions. Okay, so whatever angle between two segments obeys to this rule. Okay, so it means that not only angles measured in the horizontal orientation like XY plane, but also angles measured in vertical. Okay, so this curve is more, let's say, suitable for our purposes in this deformation process. Okay, so next step. We can also, well, there was an image that I published when I was announcing this course, which is basically derived from this exact example, and that image was actually using a sphere. So I can use a sphere, and eventually I will give it a radius like that compares to our actual size of the object. Remember that this script here, the values that we are using for each of our goals also depend on the scale of our design, on the scale of our design, and on the amount of segments that we create for our curve. So each time you change design, change scale, or change the resolution of our polyline, you must tweak the values of your goals. Okay. So once I have this, I can, for example, extract some isocurve from this surface, and I would use an MD slider. Let me reparameterize this. So we have these two curves. I want the horizontal one. So this is a circular curve, and this is a arc-like curve. So I need the U curve. And I want the U curve to behave like we were discussing here. So what I would do right now would be to simply take the sphere and use it as surface, and take the U isocurve and use it as a curve. Okay. So my isocurve is being also projected onto the sphere, which is unnecessary actually. So I can simply skip this passage here. I can also send directly the U curve to my rebuild curve, so avoid using this. I will get rid of this change here. So it's just to reproduce one interesting shape that I was publishing last week. So yeah, I think that everything is already properly set. So on mesh is selected as collision or constraint. So if I do this, we should start getting some deformation for this circle. Let me see if we have to tweak something, because I think this curve is larger than the previous one. So eventually we must tweak the length line and the goal. Let me double check what's the length actually of these segments. You always have to, yeah, you see that it's already deforming, but I think that the segments were quite larger. 0.09, yeah. It looks like nothing, but it's already something. So you see that we are already getting this kind of deformation, as the original curve was a circle and the underlying surface is a sphere. We should get some nice undulation, some nice vibration of this string here. So when we start increasing, for example, the length of this, you will have this kind of expansion along the sphere, like this. And then there is also the collision that you can adjust in order to avoid, let's say, too much the curve to get much too close to each different portion. So if I get rid of the preview of the sphere, you see that this is what I was publishing last week. So it's very easy to obtain this kind of design, and also, well, of course, the featured image for the curves is actually this same script, but with an angle. So if you start increasing the angle here, you will see that this thing tends to be more polygonal than the previous one, and you have this this line, which is actually the icon for this course. Okay, so it's very simple to obtain this kind of design once you know the script, of course. Okay, so let's go back to 0 here. Let's unroll this curve. You see that now it's totally irregular, but it tends to smoothen up and go back to its original configuration. And also let's decrease this rest length. And also let's decrease this. I want to go back to a more, let's say, controlled situation, so that when you release the simulation on your own, then you won't have any problematic behavior. You see how let's say, slow is this deformation at the beginning, but then once it happens in one point, it propagates all along the curve. Okay, and so you have this curve dancing around like this. Once you see this, then you can start tweaking the parameter very gently. Okay, so let's stop this. Let's reset. I told you I'm going to get rid of this, so go back to this curve. Disconnect the surface and disconnect the curve. So we have exactly the same configuration. Well, I will leave this like an option. Okay, so if you want, you can play around with this second option that you have for surface, and both the surface and the curve. Okay, so yeah, I will leave it like here. And let's Control G and Control E all of this. Okay, so this is a reaction diffusion mechanism. Of course, we are considering this like a two-dimensional problem. Well, both geometrically or parametrically, because we are considering like filling a square flat area or a two-dimensional domain like an organic or like a surface, a generic surface. Even if the surface is three-dimensional in space, its domain is always bidimensional. So we're always filling a two-dimensional domain, okay? Be it flat or organic, it doesn't matter, or spherical. But this is something that also can happen in three dimension, okay? So, for example, let's see if we can easily get to this point. What I'm going to do, I'm going to copy-paste this. Let's copy-paste it. So in order to avoid wasting too much time, I'm going to get rid of this. Of course, I don't need it. And I'm going to reactivate this script here. So I don't want to work with a flat curve or projected curve or a surface anymore. Okay, so I don't want this. What I want is to work with some NURBS curve and with some points that I can place like this, for example, like 3, 4, 5, 6, 7, 8, 9, and 10. Why not? And then what I'm going to do, I'm going to take this point and move it up, and also something like take this point and move it up like this, and also like this, and also like this. So creating a three-dimensional curve, more or less, in a given region of space. Okay. So I want to use this curve, actually, three-dimensional curve, totally organic. And also, what I want to do, I want, in this case, as I don't have now I don't have a boundary, or I cannot consider this boundary anymore because the curve is not lying on the same plane. So I will get rid of this, and I don't even have an underlying surface. Okay, so I cannot use any of this. So what I can do is actually use another constraint, which is a Gauss collision. So I'm going to use a solid point collide. Keep a set of points outside or inside a given mesh. Okay, so I have my points are all the vertices. Well, actually, these vertices here. If we want to consider a periodic curve, we must still work with the call index. So in this case, eventually, I can use a periodic curve like this one, but I have to tweak a little the position of these points in order to avoid this kind of extreme situation. So I am doing something like this. Okay, it's not strictly necessary, but it keeps things a little more regular. Okay, so what I can do, I need a solid. Okay, so I will take, for example, a bounding box for this three-dimensional curve, and eventually I will calculate the volume of this one like this, and I will scale this bounding box from its centroid with a slider like 1.1, like this. And so I will have this bounding box a little wider than the curve itself. Okay. So what I want is our vertices, which are this one, points, to collide with a solid. Remember that solid asks for a B-rep or mesh. I always recommend that you convert this object into a mesh. In this case, it is a standard box, so the mesh B-rep is producing quite a regular shape and topology as well. And I also want this collision to be quite strong. Okay, and interior must be set to true because I want to keep all the points inside this solid. So I will invert interior. Okay, and so this is going to be my collision goal this time. Okay, so let's plug it in the collision input, and let's run the simulation. Three-dimensional deformation of this curve. The thing with this curve is that we should not get any self-intersection. So each part of this curve should stay out or away from the other part. How can we easily detect this situation? Well, eventually we can, well, of course we can no longer use the boundary surface, but once we have this curve here, we can eventually, well, let's stop the simulation from running. So we have no deformation. And I'm going to use Dendro this time, which is quite fast for converting this thing into a volume using marching cube. So I'm going to use these settings, and I'm going to convert curve to volume. So the curve that I want to convert is this one. The settings are going to be this one. And I'm going to use a voxel size of something like 0.11. Because this object is quite small. And the curve radius is going to be something like 0.40. Something like this. And if we take a look at this tube here, we should see that it never self-intersects. Let's double check. I see no self-intersection at all. So I think that we are nailing it. Even in this area, which is quite intricate, you see that the curve is always non-self-intersecting. Okay, so this is something that can be used, for example, for space filling strategy with something which is not a regular pattern. Of course, it's somehow chaotic, as you can see, but it's quite nice to, well, actually Dendro, I think it can run in real time more or less. You see that it still follows the deformation. So yes, eventually you can run this simulation in real time. Let's see. Yeah, more or less. So it's the same behavior, but actually it is happening in real time. in 3D inside a given volume. Now I'm using a box, but actually this solid point collider only asks for a solid, so you can give this object whatever type of shape you might want to use. Okay, and of course we are obeying to the same rules. So if I increase the collision radius, you see that this line tends to let's say expand, because we are increasing the distance between its points. Also there is the angle, so if we decrease the radius and start increasing the angle, for example, then this object start to have some angle between two adjacent segments, and you can see we start to get this kind of crispy behavior. Also, this angle can also affect whole chunks of curve. If you increase, for example, the strength of this angle, you will see that it tends to become more and more important. And if you increase also the size of the edges, you will see that this angle also starts to affect the curve quite much. Remember to be very gentle, because you always are at risk of producing some unstable deformations in the system. But you see that we are filling this cube with some nice irregular and chaotic pattern. Okay, so it's quite interesting as a general principle. If you want to double check that everything is working perfectly, in this case, you might want to use here in Rhino a clipping plane, which is something that is normally used when you work with this kind of complex shapes. You can use a clipping plane in order to clearly understand if you have overlapping portions of your design. But at any stage, for example, if let me see if this is something I never tried. So let me see if custom preview also work with dendro volumes. Yes, it works. So in this case, you can see that this helps understanding if you have some self-intersection, because when you see, for example, that this tube is actually self-intersecting, it's easy to detect it by moving this plane here. So let me get rid of this. So you see that you have this kind of extremely nice pattern coming from this definition, actually. So it's also a three-dimensional behavior. Okay, so you don't necessarily have to work on a plane or onto a underlying surface. Also, a given volume will work. Okay. Yeah. So, well, actually, I think that working with the angle initially, you see that this is becoming quite unstable. So I recognize this because sometimes you will see that the dendro volume become like it's evidently joining in different parts. Okay, in some portions, and this is due to the angle. So always remember, don't play with the angle before you have reached the let's say some equilibrium phase. Okay. So this curve will tend to expand sooner or later, and if it doesn't, you can simply increase the collision angle, yeah, and then decrease it. When you see that the curve starts to expand, you decrease the collision angle in order for this deformation to happen like slowly, like this. And once you have reached the desired result, let's say that this is the desired result, then you have the possibility to play around with this shape as much as you please. Of course, in this case, for example, the radius of our tube must be consistent with the collision radius that we are giving here, okay? Because else you will get self-intersections. When you get self-intersection in cocoon, in dendro, by the way, you can recognize it because dendro simply merges the volumes together. So you see that in this case, you have no self-intersections, but you have just like some merging going on. Okay, so that's how you recognize that the curve has become, let's say, unstable during the simulation, and then you might want to also control the separation between the different parts of the curve. So it's quite interesting to work with this behavior here. Three-dimensional reaction diffusion. Now, of course, it's very difficult to fill completely a given volume with this algorithm. What I can suggest in this case, if you want to do this, is try to use a starting object that more or less flows along or inside the whole volume, or it's at least representative of the shape of the volume. Because else it's very difficult that this object can expand regularly, more or less regularly, and occupy or fill the whole volume. Okay, so you see that it's expanding, but for example, we can already see that this corner here is not being filled. Actually, it depends on how this object evolves. Okay, but it's quite difficult that this thing can fill the whole space, the whole volume. Okay. It works. It doesn't self-intersect. Well, here it's getting too close, but I think that this is something that depends also on the value that I'm using here. I can increase this in order to avoid or try to avoid self-intersection, but also I forgot to decrease the length here. That's why you saw that some self-intersections were occurring. But you see that I managed to solve the situation. I acted quickly, so I could recover the self-intersection in that case. So yeah, you see that that it's quite difficult that this object produces some kind of regular pattern inside the volume, but you can try and fill the volume with, let's say, quite a good, let's say, result. So what I was suggesting is that instead of using some organic shape, you could use something that adapts to the shape that you want to fill. So, for example, I don't know, if we are using this kind of box here, what we could do eventually would be to create something like I don't know, polyline initially that simply runs like this, and eventually like this, and this, which is very little effort. Okay, and then we can go here and move it a little up, and then copy it a little up, and then simply join like this with this endpoint and this with this endpoint, and then create this kind of unique. Of course, you can also create like serpentine, like also vertically, but this is just for having a quick base curve. And then I can also, instead of working with a random curve, I can work with this curve here, set one curve, internalize, and get rid of these. And what I'm going to do, I'm going to create a switch here. So I will leave you also this alternative. So if you want to work with the original curve, you plug this. If you want to work with a new curve, you plug this one. Okay. And of course, here you must reset almost everything, and also eventually increase the size of the bounding box in order for this curve to lie on the inside. But anyway, this is actually the original curve, and now you can run the simulation. I'm going to save this, run the simulation, and you will, oh, okay, well, we have to change things a little. Remember that when you change the geometry, you must tweak all the aspects. So one thing that you can do is to leave this length here with a panel always visible in your definition. Eventually get rid of panel, paths, and indices, because you just want to have an idea of what's the value of the length of your segments. Okay, so you see that we are already almost multiplicating for 3 by 3 the length of these segments. Okay, so it's already quite a big value, this one. So let's try and work with small values, and then also this one, it was already too much. Okay, so let's work with this. Okay, so let's, well, also in this case we still have some huge, let's say, change in this shape. You see if I have also some other parameter here. No, I don't think so. Oh well, actually the smooth. Um, yeah, you take a look. This is interesting because this line is actually made up of straight portions, and then suddenly you have these 90-degree angles, right? So if you run the simulation, you would see that things become to go bad, extremely bad, in the vertices of this polyline. You see how the deformation starts to expand from the vertices. This is because of this angle here. So this angle 0 is actually trying to smoothen these vertices at first. And so it propagates, all the deformation propagates from these areas. And it's also very strong. So let's try and see if we can decrease this. Yeah, you see that now it's more or less under control. Okay, but eventually it is also already affecting the simulation too much. Okay, you see that here things are starting to get problematic because the curve is already going dangerously too close. But I still wouldn't say this is a self-intersection because we have a very small radius. So eventually it's the radius of dendro that it's too high. So you can see that actually the curve is not self-intersecting. Okay. So yeah, I think that with that, simply by decreasing the strength of the smoothing, then we already got rid of the initial problem. Okay. So if you do this, you already have an initial configuration that is suitable for occupying the whole volume. This is something that I am pointing out because we will find it again later in the mesh differential growth, which is a little more interesting when you want to um, fill a given volume with a shape. Okay? Also because in terms of let's say production or real life products, be it at whatever scale you are working, producing this kind of object here made up of one single wire or thread, it's almost impossible if you think about it. Okay, the only thing that you can do with this is eventually 3D printed with some SLA or SLS technology, eventually giving this quite a larger amount, a bigger amount for its thickness, because this way is way too thin. So eventually you can also get some kind of shapes like this. Okay, so you are filling the space, this volume randomly or in a chaotic way with a line, and then you give thickness and you get a solid object, and then you can produce this. But also, once again, this is just for some prototyping or some 3D printing process. Okay, it's very difficult to produce this, for example, on large scale. But anyway, reset this, and well, I will leave you with the option. You can work with either one curve or the other one. Just remember that in that case, also the angle value and the angle strength can be a critical parameter for the simulation. So let's once again let's go with very slow values. Reset this, and I will leave it with the original curve so that you can play around with this one. Okay, so that's it for the reaction diffusion behavior, both in 2D and 3D, but based on curve. So let's switch to another topic, which is going to be, well, way more interesting from my point of view, which is the differential growth applied to mesh. As the last topic, we're going to talk about differential growth in mesh object. This is somehow a particular subject because we need two different specifications. The first one regards the mesh representation. We are used to think about mesh objects in terms of polygons. So we define a high resolution mesh or a low resolution mesh by the amount of polygons that it has, and also in terms of polygons, we are used to distinguish between triangles, quads, and eventually enagons, which are polygons with more than 4 sides. This representation is not good for mesh growth of differential growth because of a particular topological consideration. So let's simply represent a standard mesh with polygons. I will use only quads, but this is basically the same if you consider just quad meshes or mixed meshes with triangles and quads. If you consider a quad, for example, what should happen inside this mesh for creating some kind of growth behavior would be that specific regions of the mesh should increase the resolution. So, for example, let's say that we want to expand this mesh inside a given volume, okay? And this volume allows expansion, for example, only in this area of the mesh. I don't know, maybe because the container, the volume of the container has some kind of, I don't know, tower here with correspondence to these two polygons. So in order for this mesh to expand inside this the available volume, this polygon or this part of the mesh should simply be able to, let's say, move inside the volume, the given shape. And in order to do this, the mesh cannot maintain its original resolution, because in that case, for example, well, basically you will only have the possibility for these vertices to move inside this shaft, for example, like something like this, move inside this shaft, but you will maintain the resolution. So if this vertex moves up like this, then this edge would simply pull the other vertex, and eventually you will get this effect. So when you want to produce some kind of growth or differential growth algorithm with a mesh, you must increase the resolution. And if you use quads, for example, like this, think about how could you subdivide a quad. Well, eventually you can subdivide it like this, with or without smoothing. This is not the point, okay? But you subdivide a quad like this, and eventually then you subdivide it again like this, okay? But if you do this, you are producing some disconnection, topological disconnection between this original quad and the neighbors, because you are creating vertices along this edge that don't have correspondence on the other side of this edge. Okay? So the standard mesh representation is not good for producing some differential growth behavior, and therefore we must change to a different mesh representation, which is called the half-edge representation. Why this is a better approach? Well, first of all, half-edge mesh representation is based on triangles. So we are only considering mesh whose polygons are triangles. And if you consider, for example, a mesh with triangular polygons, I'm going to draw just a few of them, like this, and then eventually another vertex here, and then eventually another one here. Okay, another one here, another one here. Just a few more, like this, for example. Okay, so let's say you have this type of mesh. Now, in this case, for example, increasing the resolution only locally is possible because you can selectively increase the resolution only in the area you want to do it. For example, let's say we need a higher resolution in this area. Half-edge is a topological representation of the mesh based on the edges. So you're not considering the polygon surrounded by edges, you are considering the edge surrounded by triangles. And in this case, if you, for example, decide that you want to increase the resolution in this area, you simply split one edge, that's why it's called half edge. You split the edge in two halves, and then you have the two subdivision happening like this. So you always have triangles, okay, but only in the desired area. And once you do this, if you need more resolution here, you can split this edge, and you have another two triangles and another two triangles. So you are increasing the resolution, but locally, and not necessarily all around the desired area. Okay, so the half edge representation is better for this kind of simulation. Okay, now in order for this algorithm to be implemented, you must install a plugin which is called Plankton, and it gives you access to this kind of primitives here, which is the Plankton mesh, and it represents a list of 3D n-dimensional half-edge meshes. So if you don't have this, I do recommend that you go, for example, on the internet and you go into, I think it's on GitHub actually, but you can simply you can simply look for grasshopper plankton, plankton grasshopper download. Yeah, you will see that there is a group in the old Grasshopper 3D website here, and here you have the link to GitHub, and you download the latest release, which is Plankton 69. Okay. And it's very simple. There are 2 files inside. Just remember to follow the procedure to install it correctly in your components folder. So once you install this, you have access to this kind of representation inside Grasshopper. So it's very important that this library is loaded in Grasshopper, because we're going to use this not only for converting our meshes or our objects into a Plankton mesh, but also to access this library from within a scripting environment, because the other observation is that we are going to need some scripting, very basic. I'm going to use Python in this case, but you can easily create this script with whatever scripting languages that you feel comfortable. So how does this thing work? Okay, so let's start and create something, let's say, practical. You could also work just with Kangaroo, but the problem with Kangaroo in this case is that it would work with a standard mesh representation based on polygons. And so the only thing that you can do in Kangaroo, for example, is increasingly raise the number of polygons of the whole mesh. So after 2 or 3 steps of these loops, basically, you would come up with a mesh with a super high resolution, and Kangaroo simply crashes. So I do not recommend you try to do this with Kangaroo alone. So let's say that we want to create something like a sphere expanding inside a cube. So let's start with something very, very simple. Okay, something like this. Yeah, exactly. So these are my 2 main elements. Okay, so I want to import the surface and the vrep object. Set one vrep, and it's going to be this one. So I'm going to internalize both of them, and I can get rid of them all. I don't want to have the box visible, because this makes it a little more difficult to understand what happens on the inside. So I'm just going to use a vrep wireframe component so that I can hide the box and only see the wireframe, the edges of the box. So how do we initially convert this surface here into a Plankton mesh? Because this is the initial problem. Well, we can use in Kangaroo, well, also Kangaroo 099, you have this mesh machine component. Okay. Now the mesh machine component, I think that somebody during this course was mentioning this component. Now we can see how this component works. But first of all, I would place a toggle so that we can reset this mesh machine and we don't have it running when we start to connect things here. So I want to convert this geometry into a Plankton mesh. Okay, and you see that the output is actually plankton.plankton mesh. What you must define here is basically, well, I would say that 2 are the important, the relevant parameters here. First one is the length. This is the length, target length of the edges of the resulting mesh. So you must set this according to, well, mainly the dimension of the object that you are trying to convert. Okay? So if we consider that this sphere has a diameter of more or less 7, let's say that if we take a slider like 1, we should already start getting some result from this operation. If you fail in defining this parameter correctly, what can happen is that the mesh, you will see the preview, the mesh will slowly tend to disappear, disintegrate. Okay, but there is no particular problem. You just have to set the length for it, the target length for edges properly. And the other one is iterations. How many steps you want to obtain between the outputs. So this is basically something like a refining process. But the way to work with this that I recommend is to follow the instruction of the reset toggle, which says that you can connect a timer if you want a continuous remeshing. Okay, so independently from how many iterations you want to program, you can connect here a timer. You can also increase the frequency, like lowering this value to 20 milliseconds. Okay, so when you release this button here, then the algorithm will start to calculate. Now you can see that this object is not emitting any preview, and it's emitting a plankton mesh. So you could eventually take a mesh container and pass this output to this, but you see that it produces an error because the mesh is not capable of understanding what's coming out from this. So what you must do is take a plankton mesh, plug it here so you can see the result of this. Once you use this plankton mesh component, you can also pass the output to a mesh container. Okay, so this is tricky, but this is how it works. So plug a plankton mesh container after the mesh machine in order to see what happens during this rebuilding of your object. Okay. Now I have used a rhinosphere, which is not properly topologically is as you can see, as it is based on poles, and we already discussed this. We will have some weird behavior in these areas. Okay, but let's run this, and you will see that the remesh is capable of basically converting this in something like, seems like a geodesic dome. It's not perfectly like that because you see that triangles are somehow distorted from now and then. But you see that we have eliminated also the problem at the poles. Once you see that the result is mostly stable, then you can simply stop the timer. So this is no longer outputting actualization for the plankton mesh, and here you have your plankton mesh. I also recommend that you eventually plug here a data dam in order to isolate, for example, the result from any additional change that you do here. Okay, so what happens if I, for example, decrease this value? You will see that this mesh starts to have shorter edges, so higher resolution. Okay. Now I'm not going to work with a high resolution initial mesh because after this process I will be using some subdivision method in order to smooth them and to increase the resolution of the resulting deformed mesh. So I prefer to have quite a low resolution version of this object and then eventually increase the resolution during the Kangaroo process. So let's stop this. We can also reset it because we already passed the output to this plankton mesh. Okay, so this is the first step. And now that we have the plankton mesh, we can convert it or use a mesh container in order to work with values or primitives that can be recognized from other components in case we need it. And we can start the growth process. Now the growth process is well, absolutely something that happens over time. And handling time in Grasshopper means mostly creating loops. And for those of you who already know my other webinars, you know that I am comfortable using anemone for creating loops. So I am going to use a loop start and loop and from anemone. And what I want to happen inside this loop is that this mesh that is entering the loop will have to increase its size. And while increasing its size, I also want this mesh to increase the resolution as it grows bigger and bigger. So if I want this to happen, I have to, first of all, let's set up this loop. I normally use a Boolean toggle. You see that the loop start makes the loop start when the trigger is set to true. So if I plug this here, this is actually set to false and the loop is not starting. Okay, and the loop end makes the loop exit when exit is set to true. So if I use the same Boolean toggle here, I will have the loop not starting, but it's false, so it won't exit. So it's something like a lack of coordination. So I would use a gate not eventually. So we can have this loop at the same time not starting and exiting, okay, because it is receiving a true right now. And the number of repetitions. Now the number of repetitions in this case, in this particular case, I normally suggest to keep the number of repetitions low when programming a loop. In particularly with mesh growth, I would suggest that this slider or this amount of repetition should not exceed, for example, 5 repetitions, which is already a good number. So I would say eventually from 1 to 5. And I will keep it to 1 right now. So I want this loop to perform just 1 iteration. So what I want to program inside this loop is the reason why I need to convert this plankton mesh into a mesh here is that inside this loop I'm going to use Kangaroo to create the growth algorithm. Okay, and you know that Kangaroo only works with meshes, so I cannot work with plankton mesh. I absolutely need to convert this into a mesh, so that's why I placed this container here. But what I want here to happen is that the edges of this mesh are going to split when their length exceeds a specific value. And this will give us the increasing resolution during the growth algorithm. So we have two things happening inside this loop. One is based on plankton mesh, because we need the half edge representation, and the other one is based on Kangaroo, which needs the mesh the standard mesh representation. So what do we want to program in terms of Kangaroo inside of this loop? Well, first of all, we need to use some show component, of course. Remember that we have the mesh entering the loop and in this loop start, so it enters data and exits from the data output of loop start. Okay, so we have it here. And I want this mesh to, let's say, become visible after the simulation, so I can simply extract it like with an entwine method that we are going to create right now. So this will be the first branch, of course, of my Kangaroo input. And what else do I want to happen? I want this mesh to become elastic, of course, because I need to have some elastic resistance to keep this object connected, right? So I'm going to, but in this case we can use Kangaroo 2, there is no need to stick with the old version. So I'm going to convert this mesh into an elastic mesh. We can also create a relay here, so we avoid many cables coming out from that component here. So we have this edge length. With, I would use a length factor of between 1 and let's say 2. Okay, so length factor 1 means that the mesh is not going to expand by itself unless we apply some other force, as we are going to do right now. And also we want to set here a variable, maybe I exaggerated with the amount of decimal, but a variable strength, so we can actually define if this elastic property is more or less strong. And so we have the elastic property already set up. And then we want to, well, inflate this thing. Inflate and or have some action that makes this object expand. So there are basically, I would suggest two things. It's like what we were discussing with the curve expansion. You can use, for example, the elastic property as well as the collider, for example, to determine that each single segment of that line was going to expand. Okay. Now, in this case, we can program different things that can make this object expand. But the more intuitive one, of course, is pressure. So we want also this mesh to be subject to some pressure. I would say that this pressure could have a value, I don't know, between 0 and 5 eventually. It depends on the strength, the elastic strength that we are going to give to this object. So we have also pressure. And another thing that we were already seeing with the lines is that we can support this kind of expansion phenomenon with another thing, which is a collider. But in this case, I wouldn't use a collider because we are talking about a mesh. Remember that the collider only works with points and lines. So we must use the sphere collide in this case. So I would take the mesh, the original mesh, deconstruct this mesh in order to have access to the vertices, and use these vertices as colliders in our sphere collide. And the sphere collide, well, actually it depends once again on the size of your model, and therefore also on the length of these edges that we are getting, because if we, for example, take a mesh edges component, this is just for some preliminary analysis, okay? And then we take the length of these interior edges. It is a solid, so it has no naked edges, of course. So if we take these and we consider the average length of these lines, you will see that we are talking about 0.89. Okay, this is the average length of these objects' edges. But of course, if I change the size of this, I will get different lengths. Or if I change the resolution as well. Okay, so this is something that you might want to analyze before starting to play with this part of the definition. Okay, so let's remember 0.9, for example. Okay, so this is actually the value that we have. And so if we take a radius with that value, we are already going to obtain some kind of repulsion from between these vertices. So I'm going to take something like, I don't know, a slider between 0.5 to, I don't know, something like eventually 2, which looks a very small value, but remember that this sphere collide will act also when we are going to split the edges into halves. So if we have 0.9 now, it will become 0.45. And a separation of 2 is going to be quite a big value, okay, for the collision. And of course the strength, also in this case I'm going to take an 11 slider and populate this input here. Okay, and so this is going to be another goal. And another thing that we can program, well, that we must insert inside in this definition is the collision, because we don't want this mesh to get out of the box when it starts expanding. And this is the collision object, well, actually not the wireframe, but the box. So I'm going to mesh derep this in order to have its mesh representation. And then I'm going to use a solid point collide, which is the same component that we used with the three-dimensional differential growth with the line. So this is the solid, and we need the vertices of this object to collide with this box. We already have the vertices, they are here. So I'm going to use them also for this collision with our box. And the strength, of course, is going to be another 11 slider. Eventually this is going to be stronger because we want this sphere to absolutely stay inside this box. So we have another collision object here. Yeah, so basically I think that that this is already a good setup for our goals. And let's switch to, well, let's go to Kangaroo. I'm going to grab a solver. Not send the goals here until I toggle these to false. So I'm going to Boolean toggle, set it to false, and place a button here and reset the simulation. So we have this, and also we can just set up the whole Kangaroo block with the tree statistics and the partition list and the explode tree as well. So I'm going to partition list this with this length, and I'm going to use the explode, but I only need the mesh. So the mesh is connected to branch 0, 0, yes. So here we have the mesh, and I can turn the preview off for everything here, including the loop start. Okay, so I only see the output of Kangaroo in terms of mesh. Okay, and what I want is this mesh to enter the loop, and so the loop is closed, and we can see the result here in the loop end. Okay, now I'm only considering the Kangaroo setup. Okay, it's just in order for this simulation to start running. Okay, problem in this case is that I have two toggles. One toggle is firing the loop, and there is another one that simply makes the simulation run. So I need these two to be connected, and therefore when this is true, which triggered the loop, it becomes false, so makes the loop stay inside the loop, because this is basically this becomes false. And I want, when this is true, I want this to be true, so Kangaroo can also run the simulation. So I would connect this directly to this on. So instead of using this one, I will use this, which is, by the way, false, and I will eventually wire display wire display hidden this, so it's not disturbing the canvas. Okay, so let's reset this, and now as this the preview is connected to this toggle. Okay, so when this toggle is false, the loop is no longer receiving anything, so that's why we don't see any preview. But if I run this, then we see our mesh, and our mesh is well, already expanding, probably because of this sphere collider. Let's see if we, oh no, this is actually because of this loop. So if we take a look at what happens inside here, this simulation is actually running. So if I start to increase these, I think we already have a bigger mesh than the sphere collide, but if I start increasing, for example, the length factor, you see that this thing starts to inflate. Let's take a look at the box. The sphere collider is not affecting this, so maybe we should also double check what's happening with this sphere. Let's see if we can already work with pressure. Yeah, it's not considering the collision object. Actually, this sounds quite strange. So eventually, what I will do in this case is to stop the loop, and eventually I will reset the simulation, and I will make these two things independent. So okay, so this is actually false, so the simulation is blocked. Okay, so it's okay. I should have this. Eventually, let's decrease this. Let's also don't apply pressure, don't apply collision. Why is this object inflating actually? Well, because it should not be growing like this in this moment, because actually there is no force that would make it grow. Pressure is set to 0, rest length is set to 1, sphere collide is set to 0.5. Let's see if it is this. No, it is not. This is strange. I don't know why this thing is actually behaving like this. It shouldn't, because we have the original mesh. Actually, the original mesh, which is this one. So it is only being transferred to this output, and then goes back and then re-enter the loop. So this is something that I don't understand actually. So let's see if we can come up with a solution. This is something that this is not taking into account this solid collision. Oh, of course, rookie mistake once again. I want this sphere to stay inside the box, not outside. This is set to false. So we need to toggle these to true. That's why the sphere was immediately growing. Okay, so I'm going to use this. Let's reset the simulation and run it. Okay, now it is not growing. Okay, and so now we can use these forces as usual. Okay, so we have this collision. You see that it makes the sphere grow, and then we reach the maximum amount inside the box, and the sphere cannot escape. So I want this sphere to grow, and as the sphere grows, it will have no more space, okay, to grow inside this object. So what happens if I try, for example, to inflate it more and more? Or if I try, for example, to increase the sphere collide, you see that it has no way to escape this. But if I start increasing the resolution of this mesh, at least locally, or at least at the beginning, just to increase the resolution, then in that case the mesh will start to have some kind of deformation and grow inside this object, but not in a regular way, like in a spherical way. So let's see how we can program this behavior. And by the way, in order to have some need for this sphere to increase its resolution, we can also change the shape of this container. So let me stop the simulation, reset it. Yeah, okay. Reset the simulation, and also change this box with something different. So let's bake this again. So we have it here, and I will eventually do something like this, probably. Yep, and eventually something like this. And then join this together, and then send this back to Grasshopper. So we have this object right now, and let's internalize this. So we get rid of this thing, and we only have the wireframe representation. So if we reset everything and make this simulation run, you see that the object now is absolutely, let's say, and in a very bad way, it is growing inside this volume, because we set the length factor, we left the length factor to 2, and we left the pressure to 2.83. We have 2s radius for the sphere collide. So remember that each time you run this kind of simulation, you might want to have the values set to a smaller value, okay? Or else you are going to have that kind of quick expansion, which will produce self-intersection, exactly like with the curves. Okay? So you see that this is what happens, and this is what we were discussing. So you see that, for example, considering this corner here, you see that the mesh passes through, but it's not the mesh that is passing through, it's that the vertices are here and here. So these are the edges connecting two vertices. And Kangaroo doesn't know that the face must stay inside the box, because we're working with solid point collide. Okay. So how can we refine this thing? Okay, because you see that there is no way for this object to occupy the volume in the proper way, because you see that it starts to have this kind of problem, especially in these concave parts. So is in this moment we want to start using the half-page representation, okay, in order to improve this kind of behavior. So let's go back and stop everything. So we are back to our original mesh, and let's introduce the half-edge representation inside the loop this time. Okay, so we have the mesh getting inside the loop. We want to convert it once again into a plankton mesh. I know this sounds something weird, plankton, mesh, mesh, plankton, but this is how you must work in order for this loop to be able to receive the mesh output from Kangaroo. Okay, and once again you convert it into a plankton, and then you reconvert this into a mesh in order for Kangaroo to be able to understand what's going on. So let's say we have this plankton mesh, right? So let me also hide the output. So we have the plankton mesh, and what we want to happen is that as soon as one edge reaches a specific length that we can program or we can parameterize, then we want that edge to split into two, and the adjacent polygons, the adjacent triangles, to split into each one into two triangles. Okay, so this is where we are going to use some scripting. I'm going to use Python, so I'm going to use math script gh Python script like this. What I want to do right now, what I'm going to program here, is I normally tend to give correct numbers to variables and to outputs also. So as I'm working with some scripting, I will eventually perform the conversion from plankton mesh to mesh inside this component in order for this to output exactly the mesh that Kangaroo needs. Okay, so the A is not going to be just a variable. Is going to be the mesh result, and output is just, you might, I don't know if you are into Python already, but this is just something like debug messages, or something that you might use in order to understand when your code is, whether your code is working properly or you have some problem at what point, and so on. So I will leave it like this. And what I want to use inside this GH Python script is, first of all, I want a plankton mesh, so let's say a P mesh, and I need a value here, which is going to be the value that defines the length for necessary length for splitting a specific edge. So I would call this like split length. Okay. So I am sending this object, this plankton mesh, to the P mesh, and then I need a split length. We saw that this mesh has a length for these edges which has an average of 0.9, if I'm not wrong. So I would say that in this case, I would say that split length could be something around this. It can be more or less. Right? Because at this, as this object starts to grow or to inflate, let's say so, to expand, then the edges might reach this value, and in that case, the edges will be split into two. Okay, so we will be increasing the resolution as soon as the expansion makes the edges reach this value. So this is going to be our split length. Okay. So what we need right now is to enter this interface and start coding. I will simply get rid of all of these things because I want to start using a totally blank script. So first of all, I'm going to tell Python that I want to use Grasshopper libraries, okay? Because Plankton libraries is installed inside Grasshopper via the Grasshopper libraries. So I need Python to be aware that we want to use Plankton libraries, and this is done by importing CLR and then say CLR add reference to grasshopper. Okay, and then we want import exactly grasshopper. Yes, grasshopper. Okay, and so we have imported the grasshopper environment basically. And what I want to load now is the Plankton library. And Plankton library, I don't know if you already installed this Plankton plugin at this point. Is based on two files. When you download Plankton 69, you will find inside the zip file you will find two files, which are plankton.dll and plankton.gha, and we must import both of them inside this script. So this is going to be something like very boring, but you have to clr.add reference. Add reference to file and path, and this is going to be grasshopper dot folders dot default assembly folder plus, and the name of the file that we want to import. That is going to be, well, it doesn't matter actually the order, but let's import plankton.dll as the first one. And I'm going to need another one of these. I'm not going to type it once again, so I'm going to select, copy, and paste this, and I'm going to use, not DKK, but DLL. And I'm going to import also GHA, which is the grasshopper assembly. Okay, so this is for finding these files, and now I want to import from these files the libraries which are Plankton, import Plankton, and import Plankton GH. And then we want also to make the extensions available inside Grasshopper, and so we clr.import extensions, and this is going to be Plankton GH.Rhino support. And that's it. So this is for preparing the environment of this script in order for us now to make Python aware that we are going to work with Plankton libraries, and in order for Python to understand which functions in the Plankton library to use in order to work with the half-age representation and perform the necessary operation over the age, which is going to be something like splitting the triangle age. Okay. So now what we want to do, this script is receiving a Plankton mesh, a half-age representation. So what we're going to say is that actually analyze each of the edges, and if you see that their length or that length is larger than the split length value, then you split that triangles into two. Okay. So it is a cycle like for I in range of what? Well, let's count the half-age, the half-ages inside this Plankton mesh. So we have the p mesh dot half-ages dot count. So we are counting the amount of half-ages, and we want this cycle to run through each of these ages, and we want to analyze that if the mesh dot half-ages dot get the length of this half-age that you are analyzing, get length of I, and if this is larger than split length, this is the condition. So what you are going to do is p mesh dot half-ages. You see that this p mesh half-ages is basically the library that you are using, and the function this time is going to be triangle split split age I. So this is the operation. So run through the ages. If you find that the age number I has a length which is larger than split length, then you triangle split edge that edge. Okay, and that's it, because this is the only operation that we want to do. And as a result, we want to make the conversion from plankton mesh to a standard mesh. So I'm going to say that mesh, which is the output, is going to be plankton gh point dot rhino support dot to rhino mesh p mesh. And that's it. We can see if this code is actually ready to work. Runtime error, pmesh is not defined. Okay, we must declare the variable pmesh. I think I made a mistake because I see that I used not a capital P. Let's see if that's the problem. So let's see if we have pmesh and pmesh and pmesh and pmesh here. Test. Split length is not defined. Also, we must use where did I use split length? Because as this one, I also used a non-capital S. So I think that's the only moment we have split length available inside this definition. Yeah, that's it. Okay, so it's working. So this is the script. Actually, it's, well, as always in programming, you have a huge part of importing and preparing the environment, and then you have a very small part for the function. Well, especially in this case, I told you that this was going to be a very simple script. So let's close it, and then we have actually this, and this is outputting a mesh. So you see that it's no longer saying a plankton mesh. Okay, so the conversion is already set, and therefore I will simply move these wires here to the output of the GH Python script and send the mesh to the plankton mesh, send it inside the GH Python script, and then have this mesh outputted from this and going inside the Kangaroo simulation. So if everything is okay, what should happen, and that's the reason why I'm using only one iteration here, is that when we release the simulation, the sphere will start to grow eventually, and then it will also increase the resolution. So this happens only while the loop is going back and forth. Okay, so if I leave this to just one iteration, I already reached the maximum iteration for this loop. So if you take the counter, you see that we already reached 1. Okay, so the loop already exited. Okay, it is already out of the loop. It is stopped. The only thing that you see here is the simulation of Kangaroo. So if you keep on increasing this, for example, the Python scripting is not working actually, because the loop is not sending back the mesh to the starting part of the loop. So the mesh is not passing through the GH Python script. Okay, so this GH Python script will act only while the loop is running. Okay, so even if I take this output mesh here and, for example, take a mesh edges and analyze, for example, the length of the interior edges and the average value of these, you see that we have 1.26. So at this point we have not reached the 1.50 yet. Okay, so let's use this in order to understand what split length we must use, more or less. So let's say that we want to also inflate this mesh. Let me grab a panel so we can see it directly here, 1.34. Let's also program some kind of sphere collide. So let's increase this. You see that it's not having effect because we already have some wider separation between these points. So eventually we can also increase this to something more. This is not sorting any effect right now. Let me double check why. Actually it should. Already with 5, we already should have some effect. Nope, not even close. But anyway, it means we will go on just with this length factor and pressure. So you see that when you have this kind of
um, expansion, then the edges are starting to get to an interesting dimension. So it means that, for example, in this case, if this mesh should go back to the beginning of the loop, then GH would split each of the edges into in two, basically, because well, I don't know exactly all the values here, but I see that I have some 1.48, 1.47, 25, so not all the edges have reached this 1.5 here. Okay, so eventually, yeah, we can leave it like this, and let's see what happens. I'm going to give some times to this object here to, well, it's almost instantaneous, but consider that the loop is quite fast. Okay, so what I'm going to do, I'm going to stop everything and program something like 3 iterations. Okay, let's see what happens. So you see that now the amount of polygons is increasing rapidly. See how many polygons we have in this case. And you also see that, well, fortunately, that's why I used only 3 iterations. See the amount of polygons that we got with this split length. Okay, it's quite much. Remember that when one edge is split into 2 parts, the problem is that not only you have 2 edges instead of 1, but each edge will receive this length factor. So it's going to become instantly, it's going to become almost 2 times its actual length. Okay, so this object will expand very, very fast. Okay, so I would say let's keep this lower in order for the next generation of edges to don't increase its size too fast. Else, in the next iteration of the loop, this will going to split the edge again and again. And also, let's see if we decrease this to simple 2 iteration. Let's see what happens. Oh, I have to reset everything. Else, I will bring this reset here. So I understand I have reset, and then I can run the loop. And so you see that now we have a higher resolution for our mesh while it grows inside this object. Okay. Now in this case, for example, instead of increasing the amount of iteration, which basically it's risky because more iteration means that this object can inflate in the meanwhile, and that the GH Python code can still split and split and split iteration after iteration the edges. Okay, so I wouldn't increase this thing here for now. What I would do eventually is eventually decrease the split length a little. So let's see what happens if I set this to 1.25. Reset and run. So we should have more edge splitting going on. So this object should have a higher resolution, this mesh. We can also take these things under control by grabbing a, let's see, if I take a mesh container and send this the output mesh to this one, I can also have the mesh available here like a preview, and I can also grab a panel and see what mesh we are getting. So if I reset and run, we have a mesh with see how the amount of polygons instantly increases. So if I stop this and reset it, see initially we have 900 and then 2000 immediately. And this is just because we have reached the maximum amount of iterations. If I set this to 3, this is going to increase more and more. But this is not just, oh, it's 2170 plus 5. No, it depends on how many edges reach the splitting length. So this can increase dramatically. Okay? So that's why I'm keeping this low. And also, if I see that I have this kind of behavior, well, I could also reset everything, maintain this as the number of repetition, maintain eventually 1.25, and I could also start, let's say, increasing this a little and see what happens inside this thing. 2516 instead of 2170, so we already have more faces. So you see that this object is growing increasingly. We have a better representation of these corners here, as you can see, and also from the top viewport, also here and here, the object is starting to turn around these corners. I would eventually, let's stop this, and let's also get rid of this length. We already know how it works. So let's just see the object, okay, which is this one. It behaves like it's a soft body expanding more or less. It also has some self-collision determined by the sphere point collide. So you see that if you increase this, you can already occupy the whole volume of this thing. Okay, so now the thing is that this object is quite irregular. Okay, and of course we can you can basically obtain a more regular object by applying, for example, this was just a control panel. I don't want to see it anymore. So you can use, for example, I don't know, some Cartman-Clark subdivision in order to create a higher resolution version of your mesh. One thing that I do recommend is that you see that this Cartman-Clark component is recalculating the mesh each x milliseconds. See? Yes, this is because even if the loop has reached the amount of iteration that we program, it is still emitting the same result. Okay. So another thing that I would do eventually would be to create here a data dam once again, and send eventually this result here to the data dam, and eventually send the mesh to the data dam, and then eventually send the output to Cartman-Clark. So in this case, Cartman-Clark is no longer recalculating the mesh over and over. And so we can use, for example, a slider between 1 and 3, and so we can easily determine the smoothness also of this object. So you can see that you start obtaining some nice objects like this one. If I turn off the preview of mesh edges with Control M, then I start to see this object as it looks like, with these concavities that are mostly due to the self-collision, to sphere collide component. Okay, so if you want to have a look at this object a little more clearly, you can use a custom preview with whatever color you might want to use, but you see that this is the result that we are getting. There is also another thing that we can do, because this thing that we are doing here, like using Cartman-Clark after the simulation, is like when we were converting a high-resolution polyline into a high-resolution NURBS curve. We were not smoothing the line. We were just performing some smoothing operation in the corners of the polyline. So the trick here would be to get to a smoother result during the simulation, and not trying to smoothen the result after the simulation, because this is not going to work. So let's say we want to, let's bake this result just to have it as to use it as a comparison with the new one. So I'm going to take this and move it aside. Okay, and let's also hide this. This is not going to be affected by the simulation because we have a data dam. Okay, so I need to visualize this. And let's also reset Kangaroo simulation. Okay, so what I'm going to do right now, I'm going to introduce another goal, which is going to try and smoothen the mesh a little during the simulation. So if you go into Kangaroo 2, which is here, you will see that in Ghost Mesh you will find also a smooth function, and this smooth function needs a mesh, of course. So I will send the mesh to this smooth component, and it also needs a strength. I would say that we need some high values for the strength, because we are already using high values for elastic force, and also for spherical light, and also for solid point light. So let's use an element slider with some values here, and let's see if this already does the job. So we can reset this and run the simulation. I think this is going to be interesting, because I think I forgot some initial values, of course. When you see this, it's like having the self-intersection in the lines, as in the previous simulations with the differential growth applied to our lines. Okay, so if you see that kind of behavior, it's because of this. I would say that we need to decrease a little the sphere point collide. Okay, this was the value that was affecting this growth way too much. And so we have this object is you see it's growing, and it's also looking a little smoother than before. So now we go and take our spherical light and determine the separation between these vertices. Now this is actually not producing some relevant improvement for the smoothness of the mesh, because we are already working with the final version, the final resolution. So we should find the balance between the growth that we are programming here in Kangaroo and this splitting that occurs during the simulation. So I would say that eventually we can try to use a higher value for the spherical light, okay, like for example something like 1, and eventually increase this split length to 1.5, or eventually also to 2, in order to avoid extreme subdivisions, and let's see what happens. Okay. I think 2 is too much, because it doesn't succeed in subdividing these edges, but I think we are not too far. So eventually let's try with 1.75. I should measure once again the length, but let's do some trial and error. Well, I think let's go back to 1.5 more or less. Yeah, actually we had some subdivision. You see it because the Kangaroo simply tends to hang a little when you have some subdivision going on. Okay, because Kangaroo is receiving more and more geometry. So yeah, I think that in the end 1.5 was a good value. And we tend to have this kind of behavior. So we can also increase the spherical light a little in order to have longer edges. Let's save this file. Yeah, now it's too much. Now it's too much, as you can see. No, it's too much. So let's decrease this to 1.25. It's a little try and error, but this is how it works. Yeah, now we have some kind of balance between the two values. As you can see, the mesh tends to occupy the whole volume during the iterations. Okay, so this is the trick. And therefore, we can also send the final result to Clark and the rest of the definition. So if I stop this and reset it, and take a look at what happened here, we have this new version of our mesh, like this one, which already looks smoother. As you can see here, you have this kind of nice the smoother aspect, which was different from this one, because you see it was more crispy. Okay, like see how crispy it is in these areas. So in this case, you have this different result. Okay, so with this, basically, if you program this differential growth for your mesh, you can make a mesh with whatever shape inside whatever volume. Now, one simple consideration is this one. What I'm going to do right now, well, before going on, let me bake this. So we have two reference objects like this. Okay, so let's turn this off and reset everything. Okay, so one recommendation is this. If you have a very complex object, like let's say that I bake again this thing here, okay, and then I go onto the top viewport and create another box like this, and I take this box and move it like here and scale it like this, and do like this, and join it together with the previous volume. So let's say that we have this thing here. Now, how can we program this growth algorithm to occupy this whole volume? Because this is going to be a little more tricky. Okay, if I run this simulation, you will see that this is good for occupying the main volume, but it's very difficult that this volume tends to or succeed in occupying this smaller area, because it has already reached its final resolution, because it has already reached the maximum amount of iteration. And so Kangaroo must work with what it has. It cannot increase the resolution here with a plankton mesh, because Kangaroo cannot do this, both because it doesn't understand plankton meshes and because we are already after the scripting. Okay, so what we need to do right now is change the mesh. So if you want to work with this kind of object, what you must do eventually is something like this. Go back to the mesh machine and prepare your expanding object properly. So for example, I would say that creating a curve like, I don't know, this, okay, and have this inside the volume is already a good starting point, because we can take this curve, set one curve, internalize data, get rid of this, and convert this into a solid, like with a pipe. And this size looks quite good, actually. And with caps, I would say, I don't know, flat, round, it doesn't matter, actually. It's going to be remeshed by the mesh machine. So this is the resulting pipe, and I'm going to send this to mesh machine. And I want to see the result, okay, also with edges visible, Control M. So I'm going to reactivate the timer and let this simulation run. Okay, so now in this case you see that this thing is suffering a little during the mesh conversion. You see that it shrinks and it becomes more irregular. This is because this size for the edges is probably too high. So I would say that we need quite a higher resolution. So you see that it behaves more properly. Okay. Remember that when you do this, you will have also a mesh with a higher resolution. And so this will also affect the simulation. So let's pass these results to the plankton mesh after the data done, and let's reset the mesh machine, and we are ready to go, because now our mesh has become this one. And this is better because when we reset and run this, now everything will start from that tube, so the mesh will start to expand also locally. So it will already be filling all these areas here. Now the problem is that we have to calibrate once again the parameter here, because you see that this growth it has become exaggerated for this volume, starting with this object. Okay, so let me Let's wait for Grasshopper to understand. Yes, okay, so let's turn it to false. Let's wait for it to react. You see how many polygons and how much expansion has been generated in this case. So let's reset this, and eventually let's also decrease the sphere collider, which is the expansion force, the extreme expansion force that we are considering. So you see that everything starts to work a little more properly in this case. There is some self-intersection going on here. That's because we already reached the bottom of this box. So I would say that also this sphere collide is not working properly in this moment. So I would say that let's increase its strength. And also, if we set sphere collide radius to this small value, remember that this is not considering the mesh, it's considering only the vertices. So there is enough space between two vertices for a third vertices to pass through. So eventually this is also something that you might want to increase a little. Let's see if this produces some unwanted result. Quite better. We no longer have this kind of self-intersection here, and this thing is starting to expand and occupy this volume. Eventually, I would say that you see that this thing is starting to behave like a expanding tube. Is going to distort and occupy this area, and if you are lucky, this expansion will tend to occupy this area here. But you see that we already got some interesting growth inside this object. Once you have this, remember that the loop has finished this job, and you are still able to work with Kangaroo. So you can still work with edge lengths and so on. And so eventually expand this thing a little more. But I do recommend that you find the balance between your parameter and the iteration of the loop. So let's see with a higher rest length if this thing expands a little more, so we should have more polygons. If we don't have more polygons, then in this case we might want to decrease the split length. So yes, you see we have the same behavior more or less, so I would say 1.25. And let's see if this gives us more polygons for this mesh. I think yes, it's already becoming slower. So see how many subdivisions happened already. And this thing is going to expand inside this volume. So this shape is quite complex. You might want to create a more proper initial expanding shape rather than a simple pipe. But you see that it's already starting to behave more properly. So it's going to expand like this, expand like that. It's like a snake occupying this space. So let's, for example, pass this result to the final Catmull-Clark. So let's pass it like this. Yep, already done. And I'm going to stop the simulation and reset the simulation, and let's see what happened with this. So you see that we created this kind of nice organic shape inside these boxes here. Also, boxes don't have this process because boxes have many edges and many 90-degree connections, so this is not the best situation for this kind of organic filling. Okay, but nevertheless, you see that we already got an interesting result. One thing that you might want to double check when you work like with these algorithms is that the result that you got is, well, actually regular. So you might want to turn off Grasshopper Preview and analyze these objects. For example, I normally use a clipping plane, like in this case, whatever orientation is good. Go into shaded mode and you will see the intersection or the sections of these objects. And so if you take the clipping plane and move it, you should never see self-intersection inside this object. So organic shapes that simply grow gradually from one shape to another. If you see self-intersection, then your mesh self-intersects and it has some problems in terms of production and whatever. But if you see this kind of nice, let's say, unique sections, then it means that the object is perfectly. Oh, yeah, here's one. This one and this one. These are self-intersections. So this object basically has some topological problem as regards the mesh. And any program, any software that you might want to use for production or prototyping will simply tell you this object cannot be 3D printed or whatever. Also here. But this is quite normal because we were pushing this definition quite much. And the upper part is quite regular. So just something here in this area went wrong. But for example, these two objects here, which were more regular, are just perfect. And you can also analyze these for several angles, like for example, with a vertical cross section, you might take a look at what happened inside this object. Okay, so this is just for analyzing the final result. But anyway, this is already an extremely good result that we obtained. So yeah, basically the only suggestion is adapt the shape of the glowing object to the shape of the volume if you want to have more control over the expansion process, and also if you want the expanding object to occupy as much as possible the whole volume and all of its irregularities. Okay. Okay, so that's what I wanted to show you as regards the differential growth with meshes. I'm going just to organize this definition a little in order to have it more, let's say, easily understandable. This is the Kangaroo part. This is the Python script for plankton meshes, and then is the loop, but it's quite obvious. I'm just going to wire display this and set it to hidden because this is going to be the output. Okay, so this is the output of the whole process. And I'm going to put it like this so that we have the data dem available. Data dem in this case is like just baking something to the final output. Okay, so this is the idea. So let's move this like here, just like this, and so we can place it correctly like this. And initially, of course, we have the mesh machine part, which converts our object into a plankton mesh, which is this one. Okay. So basically, you have four blocks here: the mesh to plankton machine, mesh to plankton mesh, and then you have the loop, and then you have five actually. You have the loop, then you have the GH Python, Kangaroo, and the output. Okay, so this is actually what you need in order to create some nice differential growth for meshes. Okay, so this definition is going to be shared together with today's session. It was the last session. So thank you very much for taking this course with me, and you're going to receive your diploma in your mailbox. Just double check that the mail address info@jankadm.com is not blacklisted and is not ending in your spam box. So thank you guys. Thank you for being here. Thank you for appreciating my job, and see you.